Recording now? It's terrible. Terrible. Where's my... Here we go. So what do you guys know about urinalysis? What? Pee in a cup. That's right. Clean catch. You've heard about that. What's that? So working in the lab, we had to incorporate this. What's so funny? Nothing. So you guys are going to have to submit to urinalysis before your internship, right? You guys know that. So.
Students from the Colorado.
Yep.
Why don't they do this last?
The last?
A lot of places of employment are doing saliva instead of the pee test.
I guess they could do a saliva test, but I don't know. You got to pay for it. You just got to pass the drug test. So, first thing you're going to do is, one thing, working in a lab, you're going to have to be, well, it depends if you end up in this part of the lab, you're going to have to be performing urinalysis. So this is one of the oldest chemical tests or lab tests that have been done throughout history, right? So this is like back before they had modern medicine, people would study people's urine, okay? And they would study the physical characteristics of the urine. What kind of physical characteristics are we talking about? Huh?
Taste.
Color.
Yeah, taste.
Yeah, diabetes, it tastes.
Yeah, and that's where the word diabetes, mellitus, and insipidus comes from, right? It's because of the taste of the urine and how those are differentiated. So, what's the matter with... I've seen people on TV drinking urine all the time.
Yeah, there's like a health thing at some point where
Hey, you drink your
Discovery, I think? No.
It's like survival, I thought.
no, there was like a health thing. There was a health kick.
Oh, there was a health kick for a while drinking your own urine?
This was years ago, 5, 6 years ago.
Bear must have been part of that. So color, right? Have you guys ever looked at your urine color, ever noticed any changes?
Yes. Because I have dehydrated there.
Dehydrated, or if you've been eating B vitamins or things like that. So foam. What do you think foaminess can tell you about your urine?
Carbon dioxide.
Yeah, protein carb. Well, it's bicarb, and then that disassociates the carbon dioxide. So that's where you get the bubbles. But if you shake it and the foam lasts a while, that's an evidence of protein or lipids in your urine. Clarity. What do we mean when we say clarity? Yeah, how well you can see through it. The odor. So these are all the physical examinations. Modern day stuff, we're not going to be looking too much at odor unless it really stands out. One important thing about the odor is a lot of tests require fresh urine. So what do you think happens to urine over time?
Stale.
It's going to get stinky. Because it'll start to grow stuff that has ureases, and that'll break down the urine. So taste, like you guys said, taste is one of the, we're not going to be tasting urine in the clinical lab that you guys are going to be working in. But historically, taste was used to come up with the characteristic, and like you guys have just mentioned, that's, how the term diabetes mellitus and diabetes insipidus comes from, and how those two are different. Depends on the taste of the urine. And then the concentration of the urine also. What do we mean concentration of urine?
Density.
Yeah, well, the density, the number of particles dissolved in the urine can tell you about the concentration. And then also the volume. A lot of times you'll see 24-hour samples, so you get a set volume, you measure that volume, and then you're going to do calculations based on things like creatinine clearance, and you need to, a full day's worth of urine to do that. So. Anyways, so urine color. The normal pale yellow color of urine is due to the presence of urochrome. So it's a pigment that naturally ends up in you know, the urine gives you that normal yellow color. Urine color is going to vary most commonly because of the concentration. So you've noticed when it's really dark yellow, it's concentrated. When it's really pale or clear, it's, you know, dilute. And that could be because you're drinking lots of water or on some kind of diuretic or something like that, right? Or you got something wrong that won't let you concentrate your urine. So, but many foods, medications, metabolic products, and infections may produce abnormal colors. These are some examples of different urine colors. So in the lab, they're going to want to use descriptive terms like these, such as light yellow, yellow, amber, red, or brown, to describe the color of the urine. And there's even more colors than this. Most of these changes in urine color are going to be harmless and temporary and may be due to something like foods, like beets can turn urine into a bright red color. Dyes in foods and drinks, of course. Supplements, who's taking vitamin B supplements? And then P, it's like super neon, yeah. Prescription drugs also, and then unusual urine color can indicate infection or serious illnesses. And abnormal urine color, so some abnormal urine may not have an abnormal color. Just because it has a normal color doesn't mean it's healthy urine, right? But then likewise, normal colored urine may be pathologic. So some abnormal color may not have anything wrong with it, but the other, you know, you can't tell definitely by the color, but the color is just an indicator of something that's in the urine, right? So some pathologic color changes can result from melanin. So why would you find melanin? Anybody have any ideas of what that is? You guys know what melanin is, right? It's a pigment. So if you've got melanoma, sometimes you can end up with melanin in your urine. Homogenistic acid, which is alkatonuria or black urine disease. Indican, it's the blue diaper syndrome. Blue diaper syndrome. It's blue diaper syndrome. Both of these tend to be, they're metabolic disorders. Porphyrins, you guys know what porphyrins are? What? Huh? Iron's not a porphin, but it's held together by a porphyrin. But that would be a specific porphyrin heme, right? So porphyrins are just those ring structures that, you know, often are converted into heme, things like that. Hemoglobin and myoglobin also can indicate abnormal urine color and different things. So here's an example of some green urine. Well, yeah. So this, you can get green urine from these different drugs: cimetidine, promethazine, amitriptyline, flutamide, indomethacin, methylcarbamol. That's one that's taken commonly by people. Do you know what that is?
Muscle relaxer.
Yeah, it's a muscle relaxer. Mitoxantrone, propofol, phenylibutazone, trimethoprim, and so forth. Diseases that can cause green are bacterial infection, Hartnup disease, endokinemia, and endokinuria. And then dyes that can cause it are carbolic acid, flavin derivatives, indigo blue, methylene blue, or resorcinol. Brown can be the result of levodopa treatment, nitrofurantoin, metronidazole. And the conditions that can cause it are rhabdomyolysis. What is that? Do you guys know?
Rapid muscle breakdown.
Yeah, rapid muscle breakdown. And bile pigment can also result in that. Can you guys see that? The brown? It looks like a dark tea. Huh? Yeah. So other things that can cause it are fava beans. So you know that serial killer guy probably had dark brown urine. What was his name? Yeah, that's it. Yeah. Black. So you can have black urine. Stimulant laxatives oftentimes can cause this black urine. Conditions such as alkaptonuria or methylhemoglobin. What is methylhemoglobin? Methhemoglobin.
Urea.
Yeah. Sorry, I'm not good at pronunciation. You guys know I'm bad at words, right?
Words are good.
So why do you get methemoglobinuria? Huh?
Yeah, the iron is.
It's oxidized. So that's going to occur if you have red blood cells in your urine and you have an alkaline urine. It's going to lyse those red blood cells and oxidize the hemoglobin if it's sitting there for a while. And then that oxidized hemoglobin will have this dark color. Other ones are melanin. So, like I said, that can indicate bad things. Red. So, of course, drugs that can cause this are levodopa, nitrofurantoin, and metronidazole. We already talked about rhabdomyolysis, biopigments, kidney stones, malignancy, trauma, infection, pyelonephritis, UTI, pyelonephritis, cystitis, prostatitis, TB, and schistosomosis. What's that? Did you guys learn that in micro?
It's
There's those blood flukes, right?
Yeah.
So those are nasty little things. And I'm going to show you a picture of what one of those looks like in the urines later on in this. So yeah, fava beans. So don't eat your fava beans before you take your urinalysis, so they think you messed with your urine, put some kind of adulterant in there, right? Orange, you can have orange urine. I don't know how well these pictures are showing up. I can't really see.
It's pretty orange.
Almost looks like, yeah, Gatorade. So yeah, warfarin's up here, rifampicin, all of these drugs. Food or supplements, keratins, beta carotene, B complex vitamins, sienna, rhubarb, beets, and blackberries. Diabetes mellitus can cause this, hyperlipidemia or hypothyroidism, and porphyria. So, purple.
Wow. That's pretty. Oh, purple urine. Oh, yeah.
So certain bacteria can cause purple urine. So, and that I named those there. I'm not going to try to say them, except for E. coli, I can say, I guess, or Enterococcus species. Conditions such as Hartmann's disease, endoconemia, and endoconuria all can cause purple urine. That's pretty purple.
What is Hartmann's disease?
I don't know. I keep thinking of parsnips when I see it.
Hartmann's disease. It is dermatosis. Autosomal recessive metabolic disorder affecting the absorption of nonpolar amino acids, specifically tryptophan.
So if you're not absorbing tryptophan, it gets oxidized, or like, what happens?
Hold on. It says failure to thrive, photosensitivity, intermittent ataxia, tremors. It's pretty.
Doesn't sound like fun.
No, it's not bad.
Sounds like babies, and then they don't live very long.
Yeah.
So clarity. What causes a decrease in clarity?
Bacteria.
Anything big enough that's going to scatter the light. So not just bacteria. What other things can you find in your urine that are going to? Huh? Crystals. Precipitates form. What else? Lipids, proteins, cells. Yeah, things like that. So, and they're going to be graded basically on a scale from clear, slightly cloudy, or just downright turbid, right? So, non-pathological regions for cloudiness include mucus, sperm and prostatic fluid, squamous epithelial cells, feces, radiographic media, normal urine crystals such as urates, phosphates, contaminants like body lotions and powders, right? So it's easy to contaminate urine samples. What's so funny? I got this list straight from the book, I think. Yeah. So this is the book. I'm going to recommend it next semester, but just for this little section. So, but it probably would help you for your, studying for your boards, I guess. Because not only is it urinalysis, but all the body fluids, and there'll be some pictures on those exams, and I put some of the pictures on here. You're going to have to identify things on those board exams. And for our exam, I'll make like a matching thing with the different pictures, and you got to match them. Does that sound cool?
What is purple urine?
No, you'll see when we get to the microscopy section. So, microscopy. Pathological conditions that affect urine clarity could be red blood cells. Why might you have red blood cells in your urine?
Trauma.
Yeah, trauma, or just a bad kidney, right?
Bro, bad kidney stones.
Yeah. So white blood cells, what might cause white blood cells?
Infection.
Yeah, bacteria or yeast. Renal epithelial cells, fat, abnormal crystals, calculi. Yeah. What's the matter with my words? Calculi and pus. So. And we talked about foamy urine. I know there's some beer drinkers in here. If your urine looks like this, you might have too much protein in your urine, right? And when I was researching this, I found this website about this urologist, and he did this huge write-up about he's traveling a lot, and he's going to the airport bathrooms, and he can't help but look at the urine in all the stalls, and he's noticed just there's a lot of people with foamy urine these days. Could be. So, but it could be because they're running late, right? So rapid urination can cause foamy urine, right? But it should disperse. If it doesn't disperse, if it ends up staying like that, then there's something dissolved in there, right? So, but like we were saying, nephrologists, urologists traditionally refer to it as a marker of proteinuria, and it can be caused by other factors, concentrated urine in hot weather, kidney stones. UTIs can cause it too, right? Because you're going to have protein in UTIs. Or amyloidosis. What's amyloidosis? So the kind of amyloidosis you'd see in urine is they're going to be small proteins that end up aggregating together. So. Now, Alzheimer's is an amyloidosis degree, but that you find that in the brain, not the urine. So urine odor and taste. Historically, odor led to the discovery of phenylketonuria, and unless odor is usually strong or different, you're not going to worry about it in the lab. So you're looking for unusual odors. So old urine gets stinky and may indicate a lack of suitability for testing. So if it's really stinky, you want to call for another sample, right? Fresh specimens that are foul may indicate a UTI though, right? And then fruity smell might indicate ketones. So if it's a real fruity smell, it might indicate ketones, but just because you don't smell it doesn't mean you won't pick it up, because there's going to be chemical means to test for ketones. And PKU, do you guys know what that is? So a lot of these inborn errors in metabolism end up with really funny smelling urines. And that's because babies, or people that are born with inborn errors in metabolism, specifically phenylketonuria, they can't break down, phenylalanine. So you end up with this high concentration of ketone bodies in your urine. So, and then taste.
That's funny.
Like we were already discussing, taste was important back in the day. You guys aren't going to be tasting urine, but the taste was important, for characterizing urine based on the sweetness, right? So I just thought I would throw that one up there. So Mellitus versus insipidus. Which one is the sweet one? You guys know? Yeah, mellitus is the sweet urine. So urine concentration. So there's two ways that we're going to look at different concentrations of urine we're going to measure. One is easier, which is just measuring the specific gravity. And you guys should know specific gravity is basically the density of the urine divided by the density of an equal volume of pure water, right? And what's the standard density of water? Huh?
Isn't it 1.86?
No.
Oh, that one.
1.86, are you thinking of the temperature?
Yeah.
Yeah. So what's the density is 1 gram per milliliter. But that can be affected by what? Temperature, yeah. So specific gravity is what you're going to use most often, but the way you measure it is going to have to be adjusted for the temperature and stuff. Things have to be calibrated. But we'll talk about that in a minute. So we're going to be able to detect dehydration abnormalities and what's antidiuretic hormone influenced by urea molecules, sodium chloride, glucose, dissolved solids, and cells present. And measured by urinometry, harmonic oscillation densitometry, refractometry, or reagent strips. Possible urinary values are going to be between 1.002 and 1.040. Anything outside of that range is supposedly humanly impossible to have values outside of that range. So if you see a value outside of that range, there's something wrong with your sample or your equipment, right? So the osmolality is a more accurate method, but it's a much harder way to measure concentrations. And it's, we talked about this a little bit ago. Osmolality is the number of osmoles of the solute dissolved in the kilogram of the solvent, and urine solvent is going to be water. And it's measured via colligative properties. What are colligative properties? Can you guys give me some examples of colligative properties? This is general chem stuff. Yeah, vapor pressure depression.
Yeah. Measured by
Boiling point elevation,
yeah.
freezing point depression, things like that are all colligative properties. So those properties get altered by the number of solutes in that solution. So, and that's what we'll be measuring. Is mostly in the lab you'll be looking at freezing point depression. There are some machines that can measure vapor pressure, but you'll be looking at freezing point for the most part. So specific gravity of urine is easily determined from urinary dipstick, and that urinary dipstick I think has a range from 1 to about 1.04 or 1.35 it says here. Anything less than 1.008 is regarded as dilute. Why might you have, there's plenty of healthy reasons to have dilute urine if you're just drinking tons of water, right? So, and as specific gravity greater than 1.02 is considered concentrated urine. Conditions that decrease specific gravity can be increased fluid intakes, diuretics, decreased renal concentrating ability, and diabetes insipidus. Those are all things that can lead to dilute urines. Increased specific gravity can be decreased fluid intake. You're dehydration owing to fever, sweating, vomiting, and diarrhea. Diabetes mellitus, which is the glucose urea, so that's the sweet one, right? And inappropriate secretion of antidiuretic hormone. So osmolality is a measurement of the amount of material dissolved in the urine. It usually ranges between 50 and 120 milliosmoles per liter. So the ways to measure specific gravity is, one way is urinometry. And have you guys seen this in general chem or beer brewing?
We use that in anatomy.
In anatomy, they do this?
The hydrometer?
Yeah, hydrometer, basically. That's what that is. So, but this one's a urinometer because it's designed for urinalysis. These you shouldn't see much in the lab. Do you know why?
Automated.
you need a huge amount of volume to measure it, right? So you're going to need a big sample, not a huge, but a big enough sample. And then also, they have to be calibrated based on the temperature. So you're going to fill up the container 2/3 of the way with urine, and you're going to drop that in there. And this is weighted, and it's a hollow tube that's weighted, and it's going to descend to the level till its density, the volume it's displacing is equal to the density, and that density is going to be, you're going to measure it on a scale here that should be calibrated. So the graduation at the lowest level, urinary meniscus, correction of temperature and albumin is a must. So you have to correct for both of those. Urinometer is calibrated at 15 or 20 degrees. So for every 3-degree increase or decrease, you're going to have to add or subtract 0.001. So it's not super accurate, and you need a big sample to do it. For 1 gram per deciliter of albumin, you want to add 0.001 also. Some of the automatic urinalysis machines that they have this device built into them. So it detects the specific gravity based on harmonic oscillation densitometry. And that's based on the principle that frequency and sound wave entering the solution will change in proportion to the density of that solution. So they have this hollow U-shaped tube with electromagnetically forced into oscillation. They have coils that force the oscillation. And the rate of this oscillation is dependent on the density of the sample in the tube. So it's detected, and then you get a readout automatically of what the specific gravity is. So typically you only see these on these automatic urinalysis machines, and so you will see these in the lab probably. And that's just to let you know how it works, detecting specific gravity. We have some of these, some vet grade versions of these, and this is refractometry, and it's based on the refractive index of light. So the refractive index of the solution is going to be altered based on the concentration of solutes in that solution. And like I say here, refractive index is of a solution is affected by the wavelength of light that you're reading, concentration of the solutes, and the temperature. Again, the temperature. And it looks like this. You only need a tiny amount of sample, like a little drop, and the cover plate goes down, so you just end up with a really thin layer of the urine, so you don't need much, which is nice. And then you look through here at the light source, and then you'll read the value off of where you see the phase difference there, and that tells you the specific gravity. So, and because you're using such a small volume, typically it's going to change the temperature of that solution to equal the temperature of your refractometer at the time when you're putting it on there, because it's such a small volume, it's going to equilibrate pretty quickly. Reagent specific gravity determination. So this is what we're going to see with the reagent strips. It's an indirect specific gravity determination. Basically, all it's measuring is the specific gravity of the ionic solutes in the solution. It doesn't tell you anything about what's not ionic. But the good thing about urine is the concentration of your ions is much, much greater than your non-ionic species in normal urine, right? So it's a good way to estimate the specific gravity just by looking at the ionic species. And what happens is you have this reagent test pad adhered to an inert plastic strip. These strips look like this with a plastic thing. And it's impregnated with a polyelectrolyte, a pH indicator, and it's maintained in an alkali pH. So this polyelectrolyte, it's going to act as like an ion exchange type system, cation exchange. So what you have is that polyelectrolyte is going to donate hydrogen ions in exchange for whatever cations that are in the solution are going to adhere to it, and it's going to give up its hydrogen ions. So when it releases those hydrogen ions, what does that do to the pH? Drops the pH, which is then going to change the color of the indicator dye, pH indicator dye that's used. And you end up going from, I can't see the color, but it looks like dark green to yellow, basically, as you increase. And the results in a decrease in the test pad pH, and you see the color change, and you can read it off a scale, so it's a nice little indicator. Freezing point osmometry. So this one you might see in the lab also. Specimens poured into an analysis vial, and the thermistor probe and a stirring wire are lowered into the center of an analysis vial. So you have these different things you have a thermistor readout circuit, the thermistor itself, which is inside the urine specimen, and then you have a stir vibrating wire. So that's going to keep it stirred at a constant solution. A freezing bath that you lower the whole thing into, which will end up freezing your solution. And then that's about it. And what you do is you lower the temperature, keeping it stirred at a constant, smooth rate, and you supercool that sample. And once you get supercooled a few degrees below the freezing point of water, you're going to agitate it with this vibrating wire. It's going to agitate it, and that's going to cause, the crystals to start to form in the water. It's kind of like seeding that crystal formation. And then the heat of crystallization is going to bring the temperature back up, and then it'll level off again, and this is going to be the freezing point of your urine. Once you hit here, this leveled off point, and you can measure the difference between 0 and this. That's going to be your freezing point depression. And then once you keep going past that, it'll just start to, go off on it, keep descending on a linear pattern. But the difference here is going to be your freezing point depression. And then you can calculate the number of milliosmoles in that by measured freezing point of the sample. So the difference, and this is what colligative properties of water are. For every 1,000 milliosmoles of particle, it's going to lower the temperature by 1.86 degrees C. You knew that off the top of your head, Shafina. And you'll just solve that equation, and you'll be able to calculate the osmolarity of your urine sample. And that's a much more accurate way to do, but you need that machine to do it with, which typically the labs might have, but we don't have here. So maybe I should get one. pH measurements of urine. What might pH tell you about the urine? So we know kidneys play a major role in regulating acid-base balance. Normal urine is going to vary between 4.8 or 4.5 and 8. Average is between 5 and 6, so slightly acidic is normal to have your urine slightly acidic. Acidic urine can result from protein diet or cranberries, metabolic acidosis, diabetic ketoacidosis, starvation, diarrhea, uremia, and other poisons. Respiratory acidosis, such as emphysema, chronic respiratory disease, something like that. Do you guys know the difference between these two? So metabolic acidosis, you're developing metabolically some kind of acid that's going to lower the pH of your blood and also lower the pH of your urine. So such things like lactic acid, from working out, that's adding acid to your serum and will acidify your urine also. And ketoacidosis, the same thing. You're generating keto bodies, which is going to lower your pH of your urine and serum. Respiratory acidosis. So if you have emphysema, why might that lead to acidosis? Yeah, because your lungs tries to regulate your pH of your blood by blowing off carbon dioxide. If you have a hard time blowing off carbon dioxide, you can build up carbon dioxide in your blood, which will lower the pH of your blood, causing acidosis. Renal disease such as UTI of some kind of acid-producing bacteria, chronic renal failure can cause acidic urine. Medications in introduction. Or medication induction, not introduction. What's the matter? Ammonium chloride, ascorbic acid, methionine, and mandelic acid can all cause that. Ascorbic acid is one thing you want to worry about when you're using these strips, because they can interfere with a lot of the reactions. Any kind of reducing agent like vitamin C. Alkaline urine can result from vegetarian low-carb diets and citrus fruits. Metabolic acid alkalosis, such as vomiting or lavage. Respiratory alkalosis or hyperventilation. You blow off too much carbon dioxide, that's respiratory alkalosis. UTI of some urease-producing bacteria. So why would that decrease or, increase the pH of your urine sample? A urease-producing bacteria? Huh? Do you guys know what urease does? Huh? Yeah, you break down urea. It breaks down urea and results in ammonia concentration. So that released ammonia from the urea is going to raise your pH because it's basic, right? Renal tubular acidosis. Medication induction such as sodium bicarb is a medication that can cause induction of, alkaline urine. Potassium citrate and acetylizumide. So, blood and myoglobin detection in your urine, and that's done via pseudoperoxidase activity that these heme type groups will have, right? That's what hemoglobin and myoglobin share, that heme ring, and they have what's known as pseudoperoxidase. Who's done the intro lab or any of the protein labs, such as the ELISA? So the intro lab, there's an assay where you just take an extract of horseradish and measure the peroxidase activity. So that's the peroxidase enzyme specifically. And any of the ELISAs typically have HRP conjugated secondary antibodies for detection. And it's the same chemical reaction that we're looking at in this strip. So blood can enter, one important thing to remember is blood can enter anywhere into the urine, from anywhere from the glomeruli to the urethra. How many of you guys remember the anatomy of the kidney? Huh? So you start with the glomeruli, that's like the filters the blood, and then it goes to these loops, right? And then it's at the descending loop of Henle, and then the ascending, and then the collecting duct, something like that. I should have drawn it. I figured you guys should have had an anatomy, so I didn't include the anatomy of the kidney in this. Is that bad?
We should have those.
Anyways, so anywhere in that tract you can end up with blood. And red blood cells are going to lyse an alkaline or dilute urine. So why would they lyse and dilute urine?
Inside the cells from the first time.
Yeah, because it's concentrated in the cells, water will flow in via osmosis and lyse the cell. So there's different types. There's hematuria, which is normally what you're going to see if you have positive hemoglobin. And that's often cloudy, because it's the red blood cells. Trauma, drug therapy, strenuous exercise, renal and urinary tract disease, and extrarenal disease can all cause hematuria. Hemoglobinuria is, rather than having the red blood cells in your urine, whether they lyse or not, you get hemoglobin straight from your blood into your urine. So that can tell you something else. It's normally clear because this is cloudy. You often have whole cells, which is turbid. This is often clear because it's the hemoglobin coming straight from your blood into your urine. It's intravascular hemolysis. What does that mean? Intravascular hemolysis. So that's your blood cells are lysing inside your blood vessels. Yeah, and they still get filtered, and you end up with hemoglobin in the urine. So that extensive burns can cause this also. Strenuous exercise again, and infections. So this is much more rare than this. You'll see this a lot more often than hemoglobinuria. Myoglobinuria, that's where your myoglobinuria, that's where your muscles are breaking down. You end up with myoglobin in your blood, and that gets filtered, and you end up with myoglobin in your urine. It's more toxic to the renal tubules, so the myoglobin in the kidney is toxic to it. Skeletal cardiac muscle injury, seizures, metabolic causes, toxins, polymyositis, and dermatomyositis. And then severe exercise can cause this also, if you're exercising so much that you're totally ripping up your muscles. What were you going to say? Oh, no. Thought you were going to say something. So it's based on pseudoperoxidase activity, like I said. So you have hydrogen peroxide and TMB are impregnated on the test pad. And then if you have hemoglobin in the urine sample, those two together will react with the hemoglobin to cause, this green color to form. So, but your test strip, you can have a trace non-hemolyzed, so you have these little spots. And those indicate where specific cells are. So they're not lysed cells, they're just cells, and they react with the TMB and the H2O2, and you get little dark spots. So it'll be little spots. Moderate non-hemolyzed, you have more spots. Or you can have a trace, weak, moderate, and strong, and these would be lysed samples where the hemoglobin's in solution, so it's evenly dispersed across that test pad. Does that make sense? Leukocyte esterase detection. So you guys know leukocytes are white blood cells, right? So what's an esterase? Who? Esterases are it's an enzyme that's going to cleave an ester bond. What's an ester bond? Organic, huh? That's an ether bond. Ester bonds where you have a dehydration reaction between an acid, like a carboxylic acid, and an alcohol. So you have carboxylic acid R with the double bond. So so leukocytes usually indicate an infection. So if you have leukocytes in the urine, you might be looking for like a UTI or something, or kidney infection. Leukocyte esterase activity is due to the presence of white blood cells in the urine, while nitrites strongly suggest bacteria. So we'll look at the nitrite test next. Ester, so you got some aromatic ester that's impregnated on the reagent pad. Cleavage by the esterase produces an aromatic hydrocarbon. This aromatic hydrocarbon will react with diazonium salt that's also impregnated on the pad, and you end up with this azo dye production. And that gives this bright red color. So the amount of esterase activity you have is going to increase. The more you have, the more red dye color produced. So you understand how that works? You have some kind of ester, and it's aromatic hydrocarbon ester that's impregnated on the pad. The enzyme from the leukocytes are going to cleave that ester, produce the free aromatic ring, and then that product's then going to available to react with the diazonium salt impregnated on the pad. So produce this azo dye. So we're going to see a lot of this kind of reaction is on all these test pads, or something very similar. So. Nitrite formation. So nitrites are, a nitrogen ion, right? And they're produced by bacteria from nitrates. So nitrates you should find in the urine naturally. If you have gram-negative bacteria, will then convert the urinary nitrates to a nitrite. You shouldn't have too many nitrites in your urine. And basically you have an aromatic amine that reacts with the nitrite under acidic conditions, and it produces a diazonium salt. So rather than have the diazonium salt impregnated into the pad, you have an aromatic amine, and then it'll react with the nitrite, producing a diazonium salt, and then that's going to react with an aromatic compound that's on the pad to produce another azo dye. So, and this is just a positive or negative type test. If it's red, it's positive. If it's white or negative, there's no real scaling on that. Protein. So presence of protein or proteinuria is an important indicator of renal disease. Reagent pads impregnated with a buffer to maintain the pH of 3. So you have a high concentration of hydrogen ions that are impregnated on the pad, and you have this buffer that's going to maintain that. Proteins are going to act as a hydrogen receptor from a pH indicator. So you get this acid-base reaction occurring between the pH indicator and the protein, where the indicator donates its hydrogen ions to the protein. And that induces a color change in that indicator. So you can go from negative protein with the red all the way to a lot of protein with the blue, and that is based just on that acid-base reaction between the indicator and the protein itself. Because you have a lot of buffer in there that's going to maintain a really low pH. False negatives can occur in alkaline or dilute urines conditions. So you still could have protein in your urine, but if it's so dilute, it might be false because it's really dilute. And alkaline urine is it's not going to work because that can just strip away your protons, alter the pH. So you won't get hydrogen transfer from the dye itself to the protein. Or when the primary protein is not albumin. So proteinureas, there's different types of proteinureas. You can have overflow proteinuria, which is you have an increased amount of plasma proteins, and it just exceeds the capacity of reabsorption of protein. And those are typically temporary. Okay, renal proteinuria can be glomerular or tubular or a combination of both. Glomerular proteinuria is some disease that compromises your glomerular filtration barrier. Has anybody ever heard of postural proteinuria? So this is basically, it's urinary excretion of protein only in the upright position. So it's dependent on your posture. And this has to do with the increased renal venous pressure causes renal congestion. And normally you get less than 1.5 grams of protein released a day via this. Tubular proteinuria, the tubular capacity for protein reabsorption is exceeded. Normal tubular reabsorption function is altered. That could be one of the ways. Either it's exceeded, which could be overflow, or for some reason your tubes aren't able to reabsorb protein as they should. Post-renal proteinuria can result from inflammation anywhere in the urinary tract. So if you have inflammation, inflammation makes those tissues more able to, what? I can't think of words. Somebody tell me the word I'm thinking of. Permeable, yes. So you're able to get protein to infiltrate in anywhere post-renal. So it could be, your urethra, anything like that. Your bladder. Glucose. So the presence of glucose, such as glucosuria, indicates that the blood glucose level has exceeded the renal threshold, which is typically 350 milligrams per minute that it can absorb or reabsorb from the urine, which equals out to be about 160 to 100 milligrams per deciliter in the blood. So if your blood glucose exceeds 160 to 180, you probably end up with some amount of glucose in your urine because you've exceeded that threshold. It's a useful screen for diabetes, pre-renal hyperglycemia. Why do they call diabetes pre-renal hyperglycemia? Yeah, before the kidney. So you have the high glucose concentration before the kidney. So that's why you end up with glucose in the kidney. You could also have defective tubular reabsorption can cause glucosuria. So if there's something wrong with your tubules and you can't reabsorb the glucose, you don't have diabetes, but you have a kidney problem, right? So this test is done with glucose oxidase. It's an enzyme. Right? It's going to oxidize glucose. It's impregnated onto the reagent pad and catalyzes the oxidation of glucose to glucuronic acid, and that produces hydrogen peroxide as a byproduct. So you produce hydrogen peroxide, glucuronic acid, then the H2O2, hydrogen peroxide, is going to react with the chromogen in the presence of peroxidase to produce a colored product. So on the pad itself, you have glucose oxidase, and you have a chromogen and peroxidase all impregnated on that pad. So if you have glucose, the glucose gets converted to glucuronic acid and hydrogen peroxide. Presence of the hydrogen peroxide is then going to allow that chromogen to react with the peroxidase, and you'll get a color produced. Okay? Ketones. So ketones are excreted when the body metabolizes fat incompletely. So it's ketone urea, and it results either from an inability to use carbohydrates. Anybody think any of those diseases? Huh? I think diabetes makes it hard to use carbohydrates sometimes, right? Because if your insulin isn't working or you're not producing insulin, you can't use the glucose that's in your blood. So that's one inability to use carbohydrates. Inadequate carbohydrate intake can cause ketone urea. When might you see that? Huh? Low carb diets, or you're just starving. Okay. And loss of carbohydrates. So this reaction works with this substance, which is sodium nitroprusside. It's impregnated into the reagent pad. And under alkaline conditions, the acetoacetate is going to react with nitroprusside, producing a color change from beige to purple. What's that?
Fibrosis would probably, they probably have to take their ketones.
Yeah.
Cool. So this stuff reacts with acetoacetate, but there's other ketones that you can produce, right?
Sure.
What are the other ketones? There's 3 ketone bodies your body produces: acetoacetate, acetone,
Oh, yeah.
and what was the other one? This starts with a B, I think, right? B? No, not bilirubin. But we're going to talk about bilirubin in a minute.
Ketones, acetone,
Acetone, acetoacetate, and
is it beta hydroxybutyrate or no?
yeah, something like that, yeah.
Oh, it's
So this one reacts with the acetoacetate. So, and Shafina, you talked about bilirubin. So bilirubin's the next test, and it's a byproduct of the breakdown of hemoglobin, right? So normally your urine should contain no bilirubin, right? But the presence may be an indication of liver disease, bile duct obstruction, or hepatitis. Weren't you just studying this, Willie? Yeah. So, since the bilirubin in the sample is sensitive to light, exposure of urine samples to light for a long period of time may result in false negative tests. So, be aware of that. And what happens is the pad itself, you have a diazonium salt is impregnated in the reagent pad. So this is this diazonium salt. It's going to react with bilirubin in an acid medium to form the azobilirubin, and it changes the color from light tan to beige to pink, like what you see here. So another one of those azo reactions. But the azo dye that's formed this time is azobilirubin. Urobiligin's related directly to bilirubin. Can anybody tell me how? How does bilirubin get converted to urobilin?
It gets conjugated and goes through the liver,
Out the bile duct into the intestines.
or it's converted to
What converts it though?
bacteria.
Yeah, bacteria converts bilirubin, or the glucuronide version of bilirubin to urobilin. So it's a degradation product of bilirubin formed by the intestinal bacteria. It may be increased in hepatic disease or hemolytic diseases. So what's the difference between the two? Doesn't this go to what you were talking about? Yeah. So if you have a hemolytic disease, you got like an overflow of bilirubin that's trying to pass through your liver to then be excreted. So it's like you just produce too much. In hepatic disease, you're not able to process the bilirubin, right? Huh? I don't know. I can't hear you.
That with versus in that.
Yeah, it's one of those. I got a graph coming up soon. So, anyways, this one, this test can be there's two different methods that they test for this. One is based on the azo-coupling reaction, the other is an Urix reaction. It depends on the company of test pads that we have. Tells you which one it is. Test pads impregnated with Urix reagent, which is para-dimethylamino-benzaldehyde. Urobilinogen reacts with the Urix reagent under acidic conditions to produce a red color. So similar to the azo dye, it still produces a red color. Alternatively, the test pads impregnated with the impregnated color with diazonium salt that reacts with the urobilinogen under acidic conditions to produce a red color again. And I didn't finish that sentence up there. So. But again, they both look very similar in color, and you can measure the bilirubin concentration. So normal urine contains no bilirubin, only small amounts of urobilinogen. Conjugated bilirubin has a low molecular weight, water soluble, and normally passes from the liver into the small intestines to the bile ducts, where it's converted to urobilinogen. Therefore, conjugated bilirubin does not appear in the urine except in pathologic conditions, right? So in which there's intrinsic hepatic disease or an obstruction of the bile duct. So you shouldn't have, if you have conjugated bilirubin in the urine, then it's either going to be some liver disease or an obstructed bile duct. Indirect bilirubin is of high molecular weight and bound in the serum to albumin. It's water insoluble and therefore does not appear in the urine even in pathological conditions. Urobilinogen is the end product of conjugated bilirubin metabolism and gets reabsorbed, and you find that in the urine. And it'll get resecreted in the bile also. So. And this is this little thing I found. You don't like this? This book has a much better one, but I don't have access to the images from this book. But I really like the figure in this book. I'll show you. But I tried to find something similar, and this was the closest thing that I could find. Yeah, it's very ugly, isn't it? And busy. You should never put things like this in your presentations.
Did you scan it?
I could have scanned it, I guess, but I didn't have a scanner at home when I made this.
Well, maybe it's a scanner for you.
I got a scanner here, but that's the thing, I was at home. Here, this figure here, this is a great figure to let you see the differences in the disease states. So, but this has got everything in there. So. So, next thing we're going to be talking about is the microscopic examination of urine sediment. So you have this urine, looks a little cloudy, you want to see what's in it, what are you going to do? Huh? But before you put it on the slide, you got to concentrate it. Right? So you concentrate it by centrifugation. So you're going to start off with like 15 mils of the urine that's well mixed, so it hasn't settled in the container that it was collected in. Mix it well, take 15 mils, put it in the centrifuge tube. You want to spin it at about 450 Gs. Now, why do you want to use such a low amount of Gs, do you think?
You don't want the proteins precipitate out.
Or you don't want to lyse the cells too, right? So you're going to take the 15 mils, you're going to spin it, it's going to sediment the sediment. Okay, then you're just going to pour off like the top 14 mils or so. So you've concentrated the urine about 15 times, from 15 to 1 basically. And then you mix that up, take a small sample, put it on a slide. Now that's what we do here in this lab. I think in the hospital a lot of times, they have much finer automatic equipment that'll do this for you. And then it's real, being automated, it's got much better quality control and it does things much more exactly, so you can actually come up with concentrations of things working backwards. But if you're just pouring off 14 mils, that can vary a lot, right?
Why wouldn't you just use a pipette to go down to the bottom phase?
I don't know, this is just how I was taught to do it here.
Curious, I mean, I'm saying the things wrong. Fantastic.
So you do need some liquid there still.
It would be.
Would it? Maybe a lot of times you can't even see much of the phase.
Okay.
I don't know. So then you're going to concentrate those, put it on a slide, and then you can stain slides with different dyes that are going to increase your contrast, right? So you got, one of the most common is Sternheimer Malbin stain, which is crescent violet and saffron, or a 0.5% toluidine blue. Acetic acid is going to accentuate white blood cells, epithelial cells, while lysine red blood cells. So that's something you can do if you want to. You don't want to bother with all the red blood cells that are in the sample, but you want to accentuate white blood cells. You can just add a couple drops of acetic acid, and that'll fix that. Sudan 3 or oil red are good for fat and lipid stains to confirm that you have, fat and lipid in the urine. Gram stains, of course, for bacteria. Prussian blue, and then Hansel stain. I'm not so sure about those. I read about it last night, but now I can't remember. So, and then we got different microscopy techniques. Phase contrast, basically, it converts variations in the refractive index to variations in contrast. So what that means is you're going to change the refractive index going through cell membranes or any kind of tissue, because there's going to be a refractive index change because it's going from the aqueous media into something else, right? It's going to change the refraction of that light. These microscopes can convert that variation into contrast that you can actually see with your eyes. So this is an example of bright field microscopy, and then this is with the phase ring on of the same microscope, same picture. So you can see it definitely enhances your contrast. Likewise, polarizing microscopy. Anybody tell me about light polarization? So I talked about it. Yeah, so basically it's you use a polarizing filter, and it's only going to let the light that travels with one plane go. And certain things such as fat has bifringence, so you can just isolate that. It's going to bend the light as the light travels through it. So if you have a polarizing filter, you have one above the light source, one before the optics, and you can turn those to where you exclude pretty much any light except for light that's been polarized, or that's been bent by the fats, and you'll end up excluding everything visible except for little things like this. And those are called Maltese crosses. So it's indicative, you'll get Maltese cross formation with lipids, fats, and then also starches can get the same thing. And then there's interference contrast microscopy, which you're not going to see so much because it's real expensive, and these are good enough, I suppose. So red blood cells in the urine, they look like this, look like little donuts, erythrocytes. So hematuria is the presence of red blood cells in the urine. Erythrocytes may have been originated from the kidney, ureter, bladder, or urethra. In females, you might want to consider menstrual contamination. It's a female sample. It may lyse if the urine concentration is dilute, right? And the size is they're about 7 to 8 microns in diameter, pale or yellowish, smooth biconcave disc, no nucleus, cytoplasmic granules. And normally you're going to have 2 red blood cells per high power field, right? Less than that. So Leukocytes or white blood cells are typically going to be neutrophils, right? And they're larger than red blood cells. They're about 10 to 12 microns, contain a nucleus and cytoplasmic granules. And you can, this picture's terrible, isn't it? I was hoping you could see the granules better. Sorry. So you could have Brownian movement, which are called glitter cells. Have you seen those before?
Yeah, I remember I like that name.
You like that name, or glitter cells? Glitter cells. Normal, no more than 2. And there I have red blood cells per high power field. Can originate from any part of the urinary tract, from the glomerulus to the urethra. And that just, if you're going to find a lot of leukocytes, it's going to, basically what? You got some inflammatory process going on, which could be an infection or could be some kind of inflammation, right? You can also see renal tubular epithelial cells. They're slightly larger than white blood cells. They kind of have this, they're flat. Can you see this better than the last slide, I think? Kind of flat. Cuboid or columnar, and they have this big round nucleus that you can see here. And it could result from tubular damage, pyelonephritis, ATN. What's ATN? Huh? ATN. Not the thing where you get your money from. Yeah, salicylate intoxication or transplant rejection can all cause those. Transitional epithelial cells are about 2 to 4 times larger than leukocytes, and they have this round pear shape. I don't know, this one looks like a much better pear here. I guess this one kind of does. And they have like a tail-like projection and a large round nucleus. You know, so. Squamous epithelial cells, they're large, flat, and irregular shape. Can you see this one at all? Huh?
Yeah.
It's kind of got an irregular shape and it's large and flat. It's really hard to see these on the projection, I think. What about casts? Who here has heard of casts before? Yeah, all the interns have heard of them. What about anybody in the class? I know you've heard of a cast before. Those people you hire to make movies?
Really?
It was really lame. No, so you've seen people with like casts on their broken bones, right? So it's like when you have this liquid material, then it forms like a solid type material. So that happens in your kidneys and the tubules with different compounds that can go through there. You can get casts of cells, casts of fat, all kinds, and it could be indicative of some kind of disease process depending on the type of cast that you have. And the TAM horsefall mucoprotein is the most popular protein in the urine. It's a really small protein. It's the basic matrix of all renal casts and originates from the tubular epithelial cells and is always present in the urine. So it's always there, and it basically makes the matrix of the cast. So when casts contain only mucoproteins, they're called haline casts and may not have any pathological significance. So you might just see those just because you see them, they get formed. Red blood cell casts contain entrapped erythrocytes and are diagnostic of glomerular bleeding, most likely secondary to glomerular nephritis, right? So that's, you have nephritis concentrated at the, inflammation of the glomerulus, basically, right? So you can get red blood cells going across that way, and the casts are going to form with red blood cells. White blood cell casts, you can observe that in acute glomerular nephritis, acute pyelonephritis, and acute tubular interstitial nephritis. Huh? ATN, yes. Granular and waxy casts result from further degeneration of cellular elements. And fatty casts are seen in nephrotic syndrome, lipiduria, and hypothyroidism. So these fatty casts are pathologic if you see fatty casts. What can you use to discriminate a fatty cast from just a regular cast, you think?
One of those fat stains?
One of the fat stains, or
Contrast.
not the contrast, but the polarizing. Yeah. So, good jobs. So haline casts, basically the TAM horsefall protein, very low refractive index. They're colorless, homogeneous, and transparent. Can you see that one? Barely. I tweaked the contrast on this image so you could bring it out, because I couldn't see it on my computer until I messed with the contrast so you could see it. Cause,
A road or a...
yeah, it takes, basically casts are going to take the shape of the part of the tube they were in. So they look like little rods, basically. They're going to take the shape of that tube that they formed in. So this is found in normal urine, and physical exercise dehydration can lead to them. So. This is a waxy cast. It has a very high refractive index. So this one I didn't tweak the contrast at all because you could see it a lot easier. It's yellowish gray or colorless, smooth homogeneous appearance, short, broad with a blunt and broken ends. So you can see these are kind of broken and they're shorter and broad. Cracked or serrated edges. You see the cracks or serrades. Severe chronic renal failure, malignant hypertension, and diabetic neuropathy can cause these. So this is one of your pathological casts. So and you can tell the difference between the haline cast, because these are nice and smooth, no breaks, and they're harder to see because they have that low refractive index, whereas these have a higher refractive index and they appear kind of broken, right? Granular casts, or what that is granular, right? They have looks like there's little grains in them. And they're large, coarse granules, or you can have, fine granules that are gray or pale and yellow. And there's two different types. This is the fine one. I don't know if these are terrible, hard to see, right? But you can kind of see them. They're granular, this is fine, and this is larger and coarser. These are going to result from either breakdown of cellular casts, so you have a cellular cast that eventually breaks down and it just ends up being granular, or the inclusion of aggregates of plasma proteins like albumin, immunoglobulin light chains, and significance is chronic renal disease. As with haline casts, they can also be seen for a short time following strenuous exercise. So. Here's your red cell cast. So this is much easier to see because you can kind of see it contains the erythrocytes in there that are all kind of molded together. And they're going to stain, or they look brown to tan, indicate renal hematuria, glomerular disease, which is acute glomerular nephritis or lupus nephritis, and renal trauma can all result in these red blood cell casts. White blood cell cast, you can tell they look like cells again, but they're much larger than the red blood cells. Can indicate an infection or non-infectious renal inflammation, such as acute pyelonephritis, interstitial nephritis, and lupus nephritis. Or you can have an epithelial cell cast, which is stasis and desquamentation of the renal tubular epithelial cells following tubular damage and necrosis can cause this. So if you have stasis, that's just you don't have flow through the kidney, right? So eventually the cells, as they slough off, if they're just sitting there, they'll end up forming a cast together. And then fatty casts, and this is the one that shows you that polarized light microscopy. And you can discriminate these because you get the Maltese cross formation under polarized light. And you get fatty degeneration of the tubular epithelium, and degenerative tubular disease causes these. So. Next thing we're going to look at are the crystals. So identification of the crystals in the urine is particularly important with stone disease patients. The identification of cysteine crystals establishes the diagnosis of cystinuria, and then crystals can precipitate in acidic urine include calcium oxalate, uric acid, and cystine. Crystal precipitation in alkaline urine can include calcium phosphate, the triple phosphate, or struvite crystals. And these triple phosphate ones you can remember because they look like coffin lids. So here's some images. You have triple phosphate, uric acid are all different shapes. Cystine has these hexagons, and calcium oxalate like tetrahedral type structures. This is your uric acid. So it has many different shapes, diamond, rhombic, prism, or rosette. Those indicate those. They're going to be yellow or brown. They're very common, so it's not a big deal if you see them. It can be a normal occurrence. It's associated with increased purine metabolism. So, right, so you get uric acid as a breakdown product of purine metabolism. Calcium oxalate, they're colorless, octahedral, or envelope. Ingestion of oxalate-rich foods such as spinach, rhubarb, tomatoes, garlic, oranges, asparagus can cause these. And high intake of ascorbic acid can also cause these. Ethylene glycol poisoning also causes these. So you get too many of those via ethylene glycol poisoning. You've heard about people feeding dogs that stuff before? Yeah, they did that to one of my old boss's dogs. He was upset because he let his dogs run loose, and one of the neighbors didn't like that, so they would leave out ethylene glycol.
They leave out antifreeze.
Yeah.
Dirt, yeah. Causes renal failure.
Yeah. So it's bad.
Yeah.
So here's the cystine, and again, they look like hexagons, right? Kind of flat hexagon type. They're colorless refractile hexagonal plates. They're diagnostically important, right? Because they're going to tell you if you have cystinosis or cystinuria, basically. Leucine, they look kind of oily. Refractile yellow or brown spheroids with concentric striations. Can you see kind of like the striations going around? They're clinically significant. You see these with maple syrup urine disease, or Oast house urine disease, and severe liver disease is when you'll see these. And you'll often see them with tyrosine in liver disease. So if you see these and these, you can kind of think it's going to be liver disease, right? So this is the tyrosine crystals. They're very fine, highly refractile needles. They kind of look like needle-like structures. Black, yellow, and sheaths or clusters, and you see these in very severe liver disease or urinalysis. Cholesterol can form crystals, and they have these large, flat-type crystals with notched corners, right? So that's indicative of the cholesterol. And you see those with excessive tissue breakdown, you're going to have a lot of cholesterol you're going to excrete. Or obstructed lymphatic flow, nephritis and nephrotic conditions can cause cholesterol crystals to form. Sulfonamide looks like fans or a sheaf of needles with eccentric binding. And they're clear brown. This picture, it's hard to see. Does it look better from back there? Here's your triple phosphate, and you find this with alkaline urine. And can you tell these kind of look like the casket lids? So they're colorless prisms, 3 to 6 sides, oblique ends. They look like coffin lids. Can be found in normal urine or chronic urinary inflammation. So, and the triple phosphate, it's ammonium magnesium phosphate. Ammonium biurate, you find it again in alkaline urine. It's yellow-brown spherical bodies with long irregular spindles, kind of like this, and we can see the spindles coming off of it. And then your normal calcium phosphate, alkaline urine again, long, thin, colorless needles, one pointed end, so you see there's a pointed end here and a blunt end here. Same thing with all of these. And they're arranged as rosettes or a star, which is what those are, and they can be found just in normal urine. So. Other things you might see in the urine includes bacteria, right? So normal urine should not contain bacteria. In a fresh, uncontaminated specimen, the finding of bacteria is indicative of a UTI, right? And because each, what's HPF again? High-powered field, views between 1 per 20,000 and 1 per 50,000 mils, each bacterium, 1/20,000th or 1/50,000th of a mil. Each bacterium is seen per high power field. Signifies a bacterial count of more than 20,000 per ml. So, therefore, 5 bacteria per high power field reflects a colony counts of about 100,000 per mil. So yeast. So yeast cells found in urine, the most abundant are candidid. Candidid albicans. So you can tell I never had the pathological. Did they teach you this in patho micro too? Huh? Oh, I don't know about that. You mean in the summer?
It's only 2 days out of the week.
So yeast are most commonly seen in the urine of patients with diabetes. Why would you see a lot of yeast with diabetes mellitus? Yeah, they like to eat on sugar. Or contaminants in women with vaginal candidiasis. How do you say that again? Candidiasis. So, and these are just like the different types. You can have budding or the, what is this called? I forget. But they kind of look like red blood cells under the microscope, but you can tell if you see things like this where they kind of bud off of each other, or you have the branches, of course, it's yeast too. But when they're like this, it can be kind of hard to discriminate between red blood cells and this. And unless you see features like this where you can see them budding off of each other, then you know it's not red blood cells. Schistosoma hematobium. What? How do you say it?
I'm pretty sure that's how you say it.
No, it's not. I'm pretty sure that's how my 7-year-old son might say it. So it's a blood fluke egg, and this is the one type of blood fluke you'll probably see in the urine. The other ones you'll see in fecal matter. So you want to be able to, if you suspect that they have a blood fluke, they're going to look at urine and look closely for these. They're 50 by 150 microns in diameter, and leukocytes, eosinophils are in the background here. So just to give you an idea of the scale. Huh?
Nothing?
And then the last one we're going to look at is Trichomonas vaginalis. And it's most frequently a parasite encountered in a urinalysis. Sexually transmitted infection of the urogenital tract, common cause of vaginitis in women. Men with this infection can display symptoms of urethritis. So, and you can't see in this picture, but it has these little, you know. Yeah. So.
2 things to see
Yep. So that's it for the lecture today. Any questions?